Good afternoon, everyone. Peregrine, could you share your screen?
And good morning, good afternoon. This is Peregrine McGehee coming to you live from Santa Cruz, California.
Okay, well, thank you, Peregrine. I will just make a short introduction, all right?
Okay, all right.
So, well, hello, everyone. Welcome to another talk in our webinar series. I'd like to remember that this webinar is also being streamed live on YouTube. You can find the link on our website or access it on YouTube channel /LIneA MCTI. So today we have Peregrine McGehee from the College of the Canyons presenting the talk entitled Mapping the Milky Way and Beyond. And Peregrine, thank you very much for being with us. So the floor is yours.
All right. And first of all, I want to thank you very much for the invite to give a webinar. I have not yet walked in the streets of Brazil, so this is my closest chance so far. So thank you for the opportunity. And so for today, I'm going to be talking about one of the four main science themes that will be explored in the legacy survey of space and time that will be undertook by the Reuben Observatory, currently under construction on Cerro Pachón in Chile. And to begin with, this is not an image from Cerro Pachón. This is actually somewhat to the north. Some marvelous work of astrophotography showing extinct volcanoes in the Atacama Desert in northern Chile. Nice view of the Milky Way and our two satellite galaxies, the large and small Magellanic Clouds. So this is basically setting the stage for some of the science and some of the explorations that we would want to do as part of the LSST. So that being said, let me give you just a very, very quick introduction to myself. So I am presently with the Earth and Space Sciences Department at College of the Canyons in Santa Cruz, California, which is about 60 kilometers to the northwest of downtown Los Angeles. It's a community college, one of the major ones in the area. My own history, in the dawn of time, actually, I was a control systems engineer working on numerous ground-based telescopes and particle accelerators. In the context of working with the Sloan Digital Sky Survey, I was convinced to go back to school and pursue my doctorate in astronomy, which I completed 15 years ago at New Mexico State University in Las Cruces. And so I am now here. That's just a short version of my background. So what I want to get into today is I want to give you an introduction to the Legacy Survey of Space and Time and the Vera Rubin Observatory. I think many of you are probably familiar with it already, but I want to get a little bit more into one of the four main science themes. So as you know, the Rubin Observatory is well under construction on the summit of Cerro Pachón, just right down the ridge from SOAR and from Gemini South. And within the LSST, which is now the survey, there are four main science themes. One, of course, is answering all of our deep cosmological questions, understanding dark matter and dark energy, The second theme is identifying potentially hazardous asteroids and also looking far out into the Kuiper Belt and beyond, looking at the original construction material for the solar system. The third is looking at the transient, the variable sky, changes in brightness, changes in position. And this is one of the themes that LSST is going to be groundbreaking in, right? Because we're going to map the sky over and over again for a decade. We'll see things that we have never expected before. But coming into the final theme of the four main science themes is the formation and structure of the Milky Way. And this is going to be the focus of my presentation today. So one of the science collaborations within the LSST is stars, Milky Way, and local volume. And historically, there were two separate science collaborations, one dealing with stellar populations, the second dealing with galactic structure. And at some point, the realization came to all of us that many of the concerns, many of the themes between these two science collaborations were shared, and so they merged together. And so we're now the stars, Milky Way, and local volume collaboration. Looking at the past and present state of the Milky Way galaxy and our neighbors. And so we're going to be looking at how we're structured in working groups, what the status of this particular collaboration is, and particularly what are the things that we might be able to do, especially as we're coming into the post-Gaia era. Part one, introduction to the observatory and to the collaborations as a whole. A number of slides that I'll be adding in here actually came from presentations made at the August Project Community Workshop. So if you're there, they may look a little familiar. But what is the Vera Rubin Observatory? Well, the Survey Telescope, now christened the Simone Survey Telescope, is an 8.4 meter diameter reflector, extremely wide field of view. In 3 nights, we can observe the entire sky, but of course that's just in one filter. We'll be using 6 different filters, the standard UGRIS like we saw in SDSS, plus a near-infrared wideband. As I said, it's located on the ridge of Cerro Pachon, and it's just about 100 kilometers inland from La Serena. So it's basically the next mountain over from Cerro Tololo. Construction is well underway. It's great to see that the observatory is now looking much more like its architectural renderings. Here is a close-up of the optical support structure. The original schedule, sort of pre-COVID, was for operations start in the October of 2022. So just 2 years hence. We'll see how that schedule has to get modified due to the events in the world. But this is a telescope project that is well underway and well on its way to completion and start of operations. The heart of the observatory. Unlike many other astronomical facilities, the Reuben Observatory only has one instrument, And this instrument is a imager, a 3.2 gigapixel CCD device, constructed at SLAC in Stanford, California. And here is one of its early images, test images done in the lab of a head of broccoli. Of course, this is nowhere near the full size of the image. Remember, it's 3.2 gigapixels in size. So this is actually the detail on this, if you could zoom into it, is absolutely incredible. So I want to talk about the context of the work on the Milky Way and the local volume. And the construction funding from the National Science Foundation, the US Department of Energy, that's for construction and for operations. The science is a completely separate effort. These are self-managed, self-governed, and there are 8 of them. Starting on the top, TVS is transients of variable star, transients of variable sky. SMWLV, of course, is stars, Milky Way, and local volume. DESC is the dark energy. Survey, SSSC, for solar system objects. There's a separate science collaboration for galaxies. Yet another one for active galactic nuclei. A 7th one dealing with strong lensing. And finally, one dealing with information science. So this is more of a technology-based working group as opposed to having a specific science theme. So at least as of August, there were over 1,500 members of these 8 different science collaborations. Within stars, Milky Way, and local volume, it was, at the time, it was just shy of 200. And we sort of self-organized a number of working groups that I'll get into. These science collaborations are in various different states of organization and formality, with actually the dark energy science collaboration being the most formally structured. But you can see that there's quite a diversity in terms of the subjects that we're talking about and the relative number of participants so far in these working groups. We are spread across the entire world, 5 continents, over 20 countries. Here in the United States, where I'm speaking from, you can see at least at the time, a breakdown by state. So when we had the Project and Community Workshop in August, traditionally, we would have convened in a physical location in Tucson, Arizona, taking advantage of the hot August weather, and be several hundred people at our large hotel complex. But because we had to go virtual, we ended up with over 700 participants from virtually every time zone on the planet. So although we missed the face-to-face interaction, I think because we had so many people in an online venue, it was a very successful week. So, talking about science. Here we are, stars, Milky Way, and local volume. We're going to be able to study the structure of the Milky Way. We're going to resolve stellar populations, get information on 17 billion stars. Of course, the dark energy science collaboration is going to be working with dark energy and dark matter. With the variable sky and AGN, we're looking at transient and variable universe. And finally, through the solar system science collaboration effort, we'll be able to produce extremely complete inventories of the solar system. So no matter what your favorite branch of astronomy is, chances are through the LSST survey at the Reuben Observatory, we're going to be able to address that. So that established the context. And now I want to get into the nature, the structure of our particular science collaboration. So to begin with, in order to study the structure and evolution of the Milky Way, we have to look across the entire galactic sky, including fields that many of the other science collaborations don't have a strong reason to work in. And these, what I'm talking about, are the crowded fields, like in the disk. So, within the visible Milky Way itself, in the galactic bulge, and also in the crowded fields in the large and small Magellan clouds. There's often an impression that many of our science cases for looking at galactic structure and evolution are focused on looking at static images, perhaps leveraging off the deep coads across the survey. But there, as we'll discover, there are many explorations that make use of time domain imaging, both for time domain photometry and also for astrometry, watching the motions of objects over time. So I'm going to list some of the science that has been proposed. This is a survey. So, there's, as we found out, for example, by working at the Sloan Digital Sky Survey, even though a survey may have been designed with a particular set of science cases in mind, there's so many other investigations that you can do with this incredible data. So the broad scale science star drivers for stars Milky Way local volume, of course, is, first of all, we want to understand the assembly history and structure of the Milky Way and of the local volume members. And also, we want to be able to understand the fundamental properties of stars within several hundred parsecs of the sun. So getting all the way down into the brown dwarf and maybe even the free floating planet regime. So now I want to talk about some of the example science cases that deal with time domain. Obviously, time domain photometry. We're looking at stars. Many stars are variable. We think we'll be able to get multicolored light curves to an accuracy of 2% or better for at least 50 million variable stars. We'll be looking at studies of cataclysmic variables, so like dwarf nova systems, eclipsing binaries. We're going to find all kinds of rare types of variables just because we're looking at the sky again and again and again in multicolors. And we'll be able to grab a large samples of eclipsing binary stars. And as you remember, eclipsing binaries are great because the system is edge on. And so when you can pull your standard Kepler's third law trick out and apply it to the period and the orbital size of the binary system, you basically will know the mass because it's edge on, right? Besides looking at time-domain photometry, we can look at time-domain astrometry. We'll find all kinds of rare, faint, and high propagation motion objects. We'll look at the faint end of the stellar mass function, and we'll find, the nearby brown dwarfs with high proper motions. We'll find free-floating planet candidates. We'll be able to use trigonometric parallaxes, both with the LSST data itself and, as we'll discuss further on, by combining and leveraging off the precise data that's come out of the Gaia satellite. We'll be able to do a complete census of the solar neighborhood out to 100 parsecs based on trigonometric parallax measurements for very, very faint objects, like down to R band of 17. And time domain studies aside, when we do static science, which is also going to leverage off of the ability to do very, very deep coads, especially for 10 years of survey data in multi-bands, we'll be able to hunt for more of our dwarf satellites, not only from the Milky Way, but across the local group, like more of the M31 and M33. We'll be able to find intergalactic stars by using color combinations like the Z minus the near infrared Y color. We'll be able to identify very low mass subdwarfs and distinguishes them from the higher metallicity disk dwarfs. We'll be able to study white dwarfs and look at their luminosity function, and we'll be able to improve three-dimensional studies of interstellar extinction, which is, of course, a byproduct of the interstellar dust. But there's more, right? We'll be able to look at the chemistry and proper motion of, mid-mass, like solar mass main sequence stars out to 100 kiloparsecs. We'll be able to create deep color magnitude diagrams for about 50% of the known globular clusters. We'll be able to look at streams like from the Sagittarius dwarf and look at the chemical composition, the motions, the spatial profile of these field of streams entities. And we'll also be able to look at the halo and local group out to 400,000 parsecs using maps of our LIRA stars, which of course would be identified by the time domain photometry. So there is a lot we are going to be able to do with understanding the nature, the structure, and the evolution of our galaxy. There is a lot of work here. So when we want to talk about the collaboration, we want to talk about our structure and our present leadership. Right now, we have a single tiered structure. So everybody who's a member of the Class Science Collaboration has the same rights and privileges. Of course, as some of you are aware, once we have commissioning and operations data in, there are issues with data rights that are being resolved. But right now, we've got about 180 members. And nominally, each of our co-chairs serve for 3 years. I started just over a year ago. Will Clarkson at the University of Michigan, Dearborn, started this year. So we would think that probably next year we would hold an election. Basically, individuals could basically self-nominate. We do a polling of the collaboration, and then at that point, John Giesis at Delaware would likely rotate off. So how do we structure it? I mean, I spent some time giving you a taste of the kind of science that's involved with the Milky Way and local volume. And historically, what we've done is we've broken this up into 7 distinct science working groups, and kind of going from the nearest neighborhood out to the far distant reaches of the local volume. In order, there are the solar neighborhood, star clusters, variable stars, study of the galactic bulge, study of the galactic structure and the interstellar medium together, the Magellanic clouds, and finally near field cosmology. So I'm going to briefly touch on these in the next section. So the solar neighborhood, and this is actually, this is showing detections of a very cool brown dwarf. The current chairs are Ben Birmingham at the University of Hertfordshire and Sebastian Lepine at Chara. So that's well underway. So this is the group who's focusing on categorizing stars and everything else within a couple hundred parsecs. Then moving out, star clusters. This is actually a Hubble Space Telescope photograph of a cluster in the Magellanic Clouds. This is in the presence of, this particular working group is reforming, and we'll be looking for more interested parties who might want to chair this group. So this will be looking at both open clusters and globular clusters with LSST data. Variable stars is in a similar position, but it has a very, very tight synergy with the Transients and Variable Sky Science collaboration. Here's a classic example. This is RR Lyrae itself and a typical RR Lyrae light curve for comparison. And part of the synergies with TVS using variable stars to map the structure of the galaxy and the halo, to look at indicators for accretion and outflow, like for X-ray binaries and for protostars. Look at microlensing events and so on, because these will all inform us about the structure and components of the Milky Way galaxy and the local volume. But there's a very, very tight connection with the TVS collaboration. Galactic bulge, fairly active. The chairs right now are Will Clarkson, who is also one of our co-leads, co-chairs for the collaboration in Michigan, and Victor DePatis at Lancashire. So that's studying the stellar populations deep within the galactic bulge, another crowded field issue. And then moving out, galactic structure and interstellar medium. So like Will, I'm actually wearing a working group hat. A gorgeous image of the Milky Way in infrared from Spitzer. And Camille Olsen in Tucson is the chair of the Magellanic Clouds group, which is also concerned with study in crowded fields, especially here in the LMC. So this is this is a group that's specifically looking at neighboring objects in the local volume. So not just the structure of the Milky Way itself. And then lastly, near field cosmology. So we're looking at streams in the halo. This is a classic field of streams image derived from Sloan Digital Sky Survey data. We're also looking for new leadership for this science working group. And there's a strong connection with the dark matter program that was initiated within the Dark Energy Survey. There is a whole theme, of course, of sort of probing the nature of dark matter by looking at the structure of halos, looking at the structure of subhalos, looking for evidence of dark matter from microlensing events, looking for evidence of dark matter subhalos by looking at the structure of these accretion streams. For example, if you had a stream and a dark matter subhalo came through it, you would expect to see the tidal disruptions within that stream of stars, and so on. So many different opportunities here. So that, in a nutshell, was just an overview of our science working groups. And now I'm going to talk a little bit about our activities. So many of you have probably seen the classic image of the LSST survey footprint. And that's always shown in equatorial coordinates. But here, I'm showing you what that looks like in galactic coordinates. So the main curve here corresponds to our northern limit in equatorial. And this region of avoidance here, the round circle, of course, it corresponds to the south celestial pole. And then there's a very, very dense region that includes this toward the center of the galaxy that we're probably not going to observe either. But you can see we are planning coverage in different regions at very low galactic latitude. So within the science collaboration, one of the things that we're working on is, for the kind of science we want to do, how do we quantify that? I mean, when you do a survey, even though LSST is a general purpose survey, your cadence, so your choice of what part of the sky do I observe when, and what filter do I use, actually makes a difference to certain science cases. So being able to develop metrics that basically say, for this particular science case, how does the way I observe the sky make a difference? And the operations simulation teams have basically constructed a series of simulations of what the data stream would look like for these different cadence or mapping scenarios. Internally, we are organizing task forces. Actually, Will Clarkson has taken a big hand with that. Some of them are dealing with the observation strategy that would help facilitate Milky Way science. Sorry, dogs. Another task force that deals with understanding how to do accurate photometry and astrometry within crowded fields. And there are several different teams working on that, as well as the effort within the project. We want to be able to reach out and have liaisons with the other science collaborations with the project. And of course, we want to reach out to new potential members in the community. We have roadmap documents. The original versions of them date from several years ago, and there's a lot of information in the LST science book, which is always being updated. And several years ago, there was a call for white papers dealing with different cadence concerns for doing different science. So we're trying to take this information and formalize and re-update the science roadmaps for the stars, Milky Way, and local volume collaboration. And we also want to help our various working groups prepare to do science with the survey data. Here's an example of the collaborations we've been doing. We had a joint virtual workshop, well, part virtual, part in face, hosted by the University of Delaware last year, and that was between the Stars, Milky Way, and Local Volume collaboration and the Transients and Variable Sky collaboration. That was very productive. So, into the future. Astronomy is not a static field. It moves sometimes very quickly. And I want to talk about sort of one example of this and how the Reuben Observatory and Milky Way science may be well positioned when we start operations in a couple years. So now I'm going to put on my science working group hat. I'm going to talk about galactic structure in the interstellar medium. So this has been a very active field of late. Of course, Gaia has revolutionized our understanding of the locations and motion of the stars. DR2 came out a few years ago. DR3 is coming out at the end of this year. And then in terms of understanding the three-dimensional distribution of the extinction in our Milky Way, Green et al. Have been doing an amazing work, mostly based on pan-stars 1 data. Here's for example, their most recent publication was based on Gaia, pan-stars, and 2MASS. They did a fairly robust Bayesian analysis of the extinction. But we think that we can actually maybe do a little bit better when we add the LSST data. So here are some examples, just a few of the example results from Gaia DR2. And this is a sort of a taste of the kind of things that we should be able to improve on with LSST. One example here, there is a warp detected in the disk of the Milky Way galaxy. It precesses with a period of about 700 million years, which is about 3 times as long as the orbital period of our sun. On the right-hand corner, we've been able to detect proper motions of stars in the Large Magellanic Cloud. This is with Gaia. You can see the sense of rotation of this, small spiral galaxy. Gaia has also found evidence of a major merger based on kinematics. And there's one population here, the dense group. These are objects whose motions both the circular motion and their radial motion are consistent with essentially orbits in the galactic disk. But of course, Gaia found this whole new distribution of stars that were inferred to come from what's now called the Sausage Galaxy as a recent major merger. So this is a taste, right? This is from Gaia. So here's from LIneA et al., 2019. Here's an example. This is showing the reddening based on the R minus Z colors. And this is the cumulative mapping distances between 1/2 and 1 kiloparsec. This is the Pan-STARRS footprint. It's gorgeous detail here, right? So there's a lot of really interesting work that's helping to lay the foundation for what we expect to find once the LSST survey starts producing data. So what are our strengths? Well, you might think, well, Gaia is doing this great work. Pan-STARRS people have done this amazing work. But some of the strengths that we'll have is we'll have deeper and also multiband photometry that's going to improve our priors for stellar luminosity, right? If you look at the HR diagram, it's not uniformly populated, right? There's a clear main sequence. So having this deep and multiband photometry is going to really help nail down the initial priors for stellar luminosity. Gaia has already given us a great temporal baseline for the brighter sources that would also be in the Gaia catalog. We'll have a much longer baseline, so we'll get much more accurate information on parallaxes and proper motions. Since we're much more sensitive than Pan-STARRS, we can conceivably probe deeper into regions of high extinction and also look at the extinction distribution at greater distances, not only for galactic science, but for other programs. If we can manage to get well-calibrated extended source photometry, we could look at multi-band maps of extended regions in the ISM and more. So there's a lot of different things we can do here. Here are some predictions of what we might see. Here is a color diagram showing the main sequence stars, locus of M stars here, picking up horizontal branch stars. You can see the white dwarfs clearly. Of course, the quasars, which show up as point objects, as was learned in SDSS, are fairly identifiable on the basis of the photometry. And on the right, if we look at what SDSS found, the scale is out here about 20 kiloparsecs. So here's the stellar distribution. But with LSST, we're looking at 10 times farther out. So we're probing way out into the halo. You can see in this cartoon image, evidence of streamers, local overdensities in the halo, currently unknown dwarf satellite galaxies, and so on. And 7, participate. There's a lot of work to be done in galactic structure. I think we're going to be quite busy over the decade or so to come. So here's how you get a hold of us. Right now, our placeholder website at the lsst.org science pages is milkyway.science.lsst.org. We have on the LST mailing lists the LST Milky Way, etc., is the main email list for the collaboration. We also are doing a lot of things on the LSTC Slack workspace, and the channel that we use for Milky Way concerns is #MilkyWay. LST also has a number of community discussion forums, community.lsst.org, and the specific link down to Milky Way topics is, as you might expect, under community.lsst.org. .c.sci.milkyway. So here are some resources for contacting us. So, summary. Like pretty much every other field of astronomy, the Reuben Observatory is going to totally revolutionize it. I've only touched on a few of the possible science themes, even dealing with local volume and Milky Way evolution and structure. One thing that's been pointed out is that in the first year of operations, LSST will basically acquire more information about the sky than has ever been uncovered. So by the time the survey is done, we're going to have at least an order of magnitude, if not more, information and knowledge about the universe that we live in. And this is actually a nice picture of from the Whirlpool Galaxy. And where are we at? Great. And at the very end, I just want to give you just a construction update. Obviously, with the global pandemic, things have been on hold, but limited construction activities have resumed as of the end of last month, and work will be ramping up gradually over the next few months. I think the project still needs to discover what the impact for the commission and operation schedule is, but at least construction has restarted. So that's good, but in a very safe manner, right? And I'm going to close with this. This is taken off the web camera this morning. Nice view of the Cerro Pochon Summit with the Reuben Observatory in the foreground. So construction is still underway, and it's becoming looking more and more like an operational facility. So that is what I have. I think we've got 10 minutes remaining in the time slot. So I will open the floor for questions, either voice or by chat.
Okay. Well, thank you very much, Peregrine, for the very interesting talk. So as
you're welcome.
Well, we have no time for questions from the audience. If you are with us on YouTube, you can use the chat and I will redirect your questions to the speaker. So questions? Okay, well, I have some questions while we wait for more people. Actually, I'm very interested also, and although I'm not working now precisely with stellar astronomy, when we compare what we will have in the LSST with what we have in Gaia, I assume that LSST will not measure distances or parallaxes, will it? From stars.
Right. So LSST will go a lot deeper than Gaia, and obviously we're limited by, we're a ground-based facility with no adaptive optics, right? So we're just limited to natural seeing. However, we will be able to leverage off the astrometric data from Gaia, right? So we will be able to produce, proper motions and parallaxes.
Okay, that's nice. Also, I assume, that some people will study binary systems that, to some extent, you can also measure distances from stars. Once
Right.
you know the